It's happening again. A mysterious object, strange, fast, and from beyond our solar system, has just entered our cosmic neighborhood. Scientists are already comparing it to Oumuamua, but this one might be even more bizarre. In 2017, astronomers detected something extraordinary. An interstellar object named Oumuamua had entered our solar system. It was fast, strange, and completely defied expectations. 2 years later, another interstellar visitor, Comet 2I/Borisov, confirmed that Oumuamua wasn't a fluke. Now, in 2025, it's happened again. A new object has appeared on radar, named A/1P-I13Z. Unlike Oumuamua, which was detected 5 days after it passed Earth, this time we were ready. Spotted on July 1st, 2025, and listed by the International Astronomical Union's Minor Planet Center, A/1P-I13Z immediately drew attention from astronomers. It first showed up on the Near-Earth Object Confirmation page, flagged for follow-up. But this wasn't just another rock on an elliptical orbit. Its sharply hyperbolic trajectory indicated it wasn't gravitationally bound to the Sun, a clear signature of an interstellar origin. Preliminary data revealed an eccentricity around 6, the highest ever observed for an object entering our solar system, confirming it's not just interstellar, but one of the most extreme interstellar objects we've encountered. Objects are considered interstellar if they move faster than 42 kilometers per second, the speed needed to escape the Sun's gravity. A/1P-I13Z is moving at about 66 kilometers per second, far exceeding that limit. To verify its path, astronomers used archival Atlas survey data from as far back as June 25. With more accurate trajectory fits, the case for an interstellar origin grew stronger. Now officially cataloged as 3I/Atlas, it becomes the third confirmed interstellar object detected in the solar system. Its closest approach to the Sun will occur on October 27, 2025, at a distance of $1.40, though Earth will be on the opposite side at that time. The object's closest approach to Earth will be on December 17 at $2.40, too far to pose any threat, but close enough for observation. Afterward, it will head out past Jupiter's orbit around March 10, 2026. Early images show the object at a magnitude of 18.8, and if its reflectivity is typical, its size could be around 20 kilometers wide, larger than both Oumuamua and 2I/Borisov. However, if it's more reflective or emitting gas, this size could be overestimated. What's particularly intriguing is the potential for non-gravitational acceleration, similar to what was observed with Oumuamua. These accelerations can result from outgassing or possibly, in more speculative theories, artificial propulsion. This is why attention is turning to the James Webb Space Telescope, JWST, which can use its infrared sensors to detect the object's temperature, size, and possibly shape. The object's steep inclination, nearly 175 degrees, further suggests it's not native to our solar system. Its orbital orientation implies it may have come from the Milky Way's stellar disk, the flat plane where most stars reside. If its velocity and direction can be calculated precisely enough, we might even trace it back to its home star system. However, observation time is limited. Though it may brighten as it nears the Sun, Earth's unfavorable position means ground-based observations will be restricted. Still, combining data from JWST, other observatories, and spectroscopic analyses may reveal whether it's a comet, an asteroid, or something unexpected. Early reports hint at cometary activity, but this remains unconfirmed. Meanwhile, the Vera C. Rubin Observatory, now operational, is set to revolutionize how we detect interstellar visitors. Its decade-long legacy survey of space and time, LSSD, promises to increase the frequency of such detections, turning rare events into routine science. The observatory has already released its first images and spotted several new asteroids, including near-Earth ones. Over 400 years ago, Galileo transformed astronomy by pointing a telescope skyward. Today, we're entering a new age of discovery. The Vera C. Rubin Observatory, designed to scan the sky night after night, will catch everything from asteroids and flaring stars to the secrets of dark matter and dark energy. Named after Vera Cooper Rubin, who who helped reveal the existence of dark matter by showing that galaxies don't rotate as expected. The observatory continues her legacy. Its 10-year LSSD project aims to image the southern sky repeatedly, stacking data to track what changes, moves, or hides in darkness. Central to its mission is the largest digital camera ever built for astronomy, the size of a small car, equipped with 189 ultra-sensitive sensors arranged in 21 vacuum-sealed, chilled modules. This setup allows it to capture faint glimmers of deep space light. Each image spans 3.5 degrees of sky, enough to fit 7 full moons, and is captured in 15 seconds with just 2 seconds needed for data transfer. The LSSD focuses on 4 main goals: exploring dark matter and dark energy, monitoring a dynamic sky for supernovae and gamma-ray bursts, enhancing planetary defense by tracking near-Earth objects, and cataloging distant solar system bodies. The observatory has already delivered on its promise with breathtaking composite images, such as one showing the Trifid and Lagoon nebulae from over 678 exposures, and another of the Virgo cluster containing more than 2,000 galaxies in a single frame. It also captured 46 pulsating variable stars, just a hint of the dynamic sky it will reveal. In 10 hours of observation, Rubin discovered 2,014 new asteroids, including 7 near-Earth ones, showcasing its unmatched speed and efficiency. For comparison, all other observatories combined find about 20,000 asteroids per year, while Rubin is expected to discover millions in its first 2 years. Every night, it will scan the sky for anything unusual, including objects like Oumuamua. If similar anomalies enter its field of view, Rubin will detect them in real time. Over time, it will generate trillions of measurements from billions of stars, galaxies, and asteroids, building a dataset so vast, it will likely raise questions we haven't even thought to ask yet. Its elongated, cigar-like shape and unexpected acceleration led to intense speculation about its nature, sparking debates across scientific communities and even raising the possibility of an artificial origin. 2 years later, another interstellar visitor, Comet 2I/Borisov, confirmed that Oumuamua wasn't a fluke. Unlike its predecessor, Borisov looked and behaved more like a traditional comet, with a visible tail and a more predictable trajectory. These back-to-back detections reshaped our understanding of how frequently interstellar objects might actually pass through our solar system. Now, in 2025, it's happened again. A new object has appeared on radar, named A/1P I13Z, or more officially, 3I/Atlas. This time, however, astronomers were ready. Unlike Oumuamua, which was detected 5 days after it had already swung past Earth, A/1P I13Z was spotted early, on July 1, 2025, and immediately listed by the International Astronomical Union's Minor Planet Center. It first showed up on the Near-Earth Object Confirmation page, flagged for urgent follow-up observations. From the start, its behavior defied expectations. The object's orbital path was sharply hyperbolic, meaning it wasn't gravitationally bound to the Sun. That's the hallmark of something not native to our solar system. Early trajectory analysis showed an eccentricity near 6, far above the parabolic threshold and the highest ever recorded. Objects on such trajectories aren't just passing by. They're moving too fast to be captured by the Sun's gravity. That raised a profound conclusion. This object didn't originate in our solar system. Its velocity, estimated at 66 kilometers per second relative to the Sun, far exceeded the 42 kilometers per second escape velocity required to break free from the Sun's gravitational influence. Such speed suggests it had already traveled vast distances before even reaching our cosmic neighborhood. Within days, astronomers dove into archival data and found images of the object dating back to June 25, greatly improving the precision of their trajectory models. The result, 3I/Atlas, was confirmed to be the third known interstellar visitor. The implications of this are monumental, especially considering the object's size. If it has a typical reflectivity, A/1P I13Z could be about 20 kilometers wide, much larger than both Oumuamua and Borisov. This enormous size, combined with its hyperbolic trajectory, has fueled both scientific excitement and deep curiosity. If it begins to exhibit any non-gravitational acceleration, like Oumuamua did, scientists might once again have to entertain unconventional theories, including exotic propulsion mechanisms or previously unknown physical effects. Such deviations could arise from sublimating gases pushing the object, or perhaps, as some theorists speculate, from artificial propulsion systems, though such ideas remain on the fringe. That's why the James Webb Space Telescope, JWST, is being turned toward it. With its cutting-edge infrared capabilities, JWST could provide unprecedented detail, revealing the object's temperature, size, surface properties, and potentially even its shape. Every clue matters. Another striking feature of 3I/Atlas is its inclination, nearly 175 degrees. That steep, retrograde angle virtually rules out any solar system origin. Instead, it points toward a distant source in the Milky Way's stellar disk, possibly hinting at its birthplace around another star. If astronomers can nail down its incoming vector with high precision, they may be able to backtrack its journey and identify the stellar system it was ejected from. This object is like a time capsule from another world, and it's passing through our solar system for only a brief window. Its closest approach to the Sun will occur on October 27, 2025, at a distance of $1.40. Sadly, Earth will be on the opposite side of the Sun then, making direct observation difficult. But on December 17th, it will swing to within $2.40 of Earth, a safe distance, but close enough for ground-based telescopes to gather valuable data. After that, it will continue outward, crossing Jupiter's orbit around March 10, 2026, and disappearing back into interstellar space. This rare opportunity to study an alien visitor is happening at a time when our observational capabilities are more powerful than ever before. The Vera C. Rubin Observatory, now fully operational, is revolutionizing how we scan the skies. Designed for the decade-long Legacy Survey of Space and Time, LSST, this groundbreaking facility will image the entire southern sky every few nights, stacking billions of observations into an evolving, dynamic map of the universe. Named after Vera Rubin, the pioneering astronomer who provided the first direct evidence for dark matter, the observatory carries on her legacy by exploring cosmic mysteries. At the heart of its mission lies the largest digital camera ever built for astronomy, about the size of a small car and containing 189 ultra-sensitive sensors. These sensors are arranged into 21 modular rafts, all sealed in a vacuum and chilled to -48 degrees Fahrenheit to reduce noise. Each image spans 3.5 degrees of sky, 7 times the width of the full moon, and takes just 15 seconds to capture. 2 seconds later, the data is downloaded, making it one of the fastest and most efficient sky mapping systems in history. Its science goals are as bold as its technology: to explore dark energy and dark matter by mapping billions of galaxies, to detect explosive cosmic events like supernovae and gamma-ray bursts, to track near-Earth objects for planetary defense, and to explore the solar system's icy frontiers beyond Neptune. Its first flight images have already exceeded expectations, showcasing the Trifid and Lagoon nebulae, the Virgo cluster, and thousands of galaxies and stars in remarkable detail. In just 10 hours of operation, it discovered over 2,000 new asteroids, including several near-Earth ones. Over the next 2 years, Rubin is expected to uncover millions of previously unknown space rocks. But perhaps most excitingly, it will give us the power to detect more interstellar objects like 3I/Atlas, not by luck, but by design. It will turn rare anomalies into predictable data points. If something, anything, enters our solar system from beyond, whether it's a rogue comet, an ancient chunk of alien rock, or even a technological artifact, the Rubin Observatory will catch it. It will see what moves, what flares, and what fades. And with every pixel it captures, it will inch us closer to answers about who we are, where we came from, and whether we are truly alone in the universe. If this object truly came from another star system, and it's not acting like anything we've seen before, then we may be looking at something far more than just a rock. The question remains, is it natural or something else entirely?